Welcome back to Beyond the Comfort Zone Talking Shit with King-KAMBUF. We have something really specialized for you today. This is a deep dive into an intelligence brief from Saturday, November 29, 2025. It's titled Architectural Insights with King-KAMBUF.
And this is not your typical industry news roundup. I mean, this is a briefing put together for world-leading designer builders.
Exactly. It's blending structural physics, urban planning, environmental engineering even geopolitics.
It really challenges you to think way beyond the normal silos of the profession.
It does. And the central idea we've kind of pulled from all this dense material is that we have to fundamentally rethink what a building is.
Right, we're moving so far past the idea of architecture as just, a passive box for shelter.
We're now talking about the built environment as an active instrument.
An active instrument. I love that phrasing. It means buildings have to dynamically engage with everything around them, their atmospheric tools, hydrologic systems, and maybe most importantly, political devices.
So our mission today is to break all of this down for you. We're going to go from these huge global climate adaptation strategies all the way down to the nitty-gritty, the micromechanics of hidden structural loads.
It's going to be a pretty intense journey. The source material is layered that way, and we're going to follow that structure from the big global pulse down to the specific study questions and on-the-ground scenarios.
Okay, let's jump right in. Section 1 is all about how buildings are becoming active players in their environment, engaging directly with the air and the ground. So we're starting with this concept of the building's skin, its facade, as an environmental actor. Specifically, these things called carbon fog harvesting skins.
Yeah, and this is aimed at a really tough problem. We're talking about thermal inversions in these super dense pollution corridors.
Like in Singapore or Cairo or Sao Paulo.
Exactly. The pollution gets trapped near the ground, creating this toxic air that normal ventilation just can't handle.
And the big idea here isn't just, filtering the air. It's actually engineering the building's exterior to actively capture the pollution.
Right. The facade membranes themselves.
So how does that actually work? Like, what's the mechanism?
Well, it's more than a simple filter. These are specialized membranes, maybe polymeric, that use an electrostatic or a chemical reaction to basically attract and bond with the carbon particulates.
So they pull the pollution right out of the air.
To pull it out, and using ambient moisture, they condense it. They turn it into a heavy, controllable slurry.
A slurry.
Yeah.
Wow. So the building isn't just sitting there. It's becoming this massive, ongoing atmospheric cleanup tool.
Precisely.
But that immediately brings up a huge architectural challenge. What do you do with this carbon slurry?
And that's the design problem the brief poses.
Yeah.
You have to create a facade detail that can channel all this runoff without messing up the building's performance.
Because that's not just rain. It's got to be corrosive, right? And heavy.
It's particulate-laden, potentially toxic, and you have to manage it. You need a kind of internal gutter system that won't clog or leak or degrade the building materials, all while keeping the envelope waterproof and thermally efficient. It's a huge integration challenge.
Okay, so from the air, we move down to the ground. A really critical issue in our most vulnerable climate zones, reflexive foundations for permafrost rebound zones.
This is a direct response to a climate crisis happening right now in Arctic cities.
Mm-hmm.
Places like Yakutsk in Siberia or Nuuk in Greenland.
Where the ground itself, the permafrost that everything is built on, is thawing.
And it's thawing unevenly,
Yeah.
which is a nightmare for structures. It causes massive settlement issues. Things just break.
So the innovation here is something called reflexive pile shoes. That's a total paradigm shift. Foundations are supposed to be static, right? Rigid.
Traditionally, yes.
Yeah.
But these are different. They have adaptive mechanisms built right into the base of the foundation piles. Think hydraulic pistons or spring systems.
So when the ground settles, say, a few millimeters on one side and a centimeter on the other,
The pile shoe adjusts. It laterally redistributes the load. It adjusts its vertical position, all in real time.
so the foundation is actively hunting for equilibrium in a moving subsurface.
It has to. You're no longer designing for solid ground. You're designing for what's called a viscoelastic material, something that's part solid, part fluid. The whole challenge is making a structure that can flex and adjust while staying rigid enough to be functional.
That's incredible. Next up, we have a really clever bit of thermal engineering that turns waste into a public good. Geoactive transit roofs.
Yeah, this is about finding energy where we normally just find waste heat. Engineers in places like Madrid and Ankara are looking at their subway systems.
All that friction from the trains, the air movement, It generates a ton of heat in those tunnels.
A ton of latent thermal energy that just gets vented out and wasted.
So the idea is to capture it, to recycle it.
Exactly. Capture that friction heat and use it to warm public plazas or open spaces right above the tunnels. You're turning transit waste into civic energy.
That's a huge win for energy conservation. But what does the capture process actually look like?
Well, you'd need large heat exchangers right above the tunnel, absorbing the heat. Then you'd need an efficient way to pump that energy to the surface.
But you'd have to be careful, right? You can't just pump tunnel air into a public plaza.
No, absolutely not. You'd have to filter out any contaminants. The key is to radiate clean thermal energy back into the public space, maybe through tubes embedded in the pavement.
I have to wonder about the efficiency loss, though.
That is the engineering problem. You need super insulated transfer systems. And look, you're not trying to heat a skyscraper with this. You're just trying to raise the surface temperature of a plaza by a few degrees, enough to melt snow or just make it more comfortable on a cold day. It's localized, but the civic impact could be enormous.
This theme of dynamic response just keeps coming up. Let's dig into these adaptations for dynamic conditions, starting with drift-stabilized modular housing.
Right, so in places that are seismically active, like Japan or Portugal, building something that's just purely rigid can be really expensive, and sometimes it's not even the best approach.
So these prototypes are designed to move.
They use what are called drift-tolerant joints. It allows the different modules of the house to slide against each other in a controlled way during an earthquake. It absorbs the energy.
Okay, so the structure survives the shake, but the brief points out a critical and often overlooked problem.
Utilities.
The utilities. How do you stop the plumbing and the gas lines from rupturing when the boxes are shifting around?
That's where the really detailed engineering comes in. You need utility couplings that are super flexible. Think of like serpentine loops of pipe that can stretch and compress in multiple directions without breaking.
So the building's life support systems have to be even more elastic than the frame itself.
They absolutely have to be.
All right, next is a material science breakthrough that, honestly, it messes with your head. High salinity coastal concrete.
It's completely counterintuitive. For centuries, salt has been the absolute enemy of reinforced concrete.
Right, it gets in, it corrodes the rebar, the concrete spalls off. It's a disaster.
But now, labs in Israel and around the Mediterranean are developing formulas where salt is actually used as a strengthening catalyst.
How's that even possible? How do you turn the enemy into an additive?
The mix is very, very specific. It has additive specialized polymers that react with the chloride ions from the salt water, and instead of causing corrosion, that reaction encourages the growth of these super dense crystalline microstructures inside the concrete.
So it's filling in the gaps, making it denser.
It fills the microvoids, making the concrete stronger and less permeable to future attack. It's a material that is literally optimized by the very environment that used to destroy it.
The implications for waterfront infrastructure are just massive. Piers, jetties, breakwaters.
All things that currently need constant, expensive maintenance. This could change the entire cost-benefit analysis for building in coastal zones.
And finally, for this section, we're looking at pre-construction, at getting smarter before you even break ground with autonomous site-mapping drones.
Yeah, in cold climates like Norway or Canada, this is becoming a critical first step.
They send up drones with thermal imaging?
High-resolution thermal imaging. And they're looking for things you can't see with the naked eye. Improper soil compaction, hidden pockets of frost or water.
It's like giving the construction site a CT scan before you start surgery.
That's a perfect analogy.
Yeah.
And the real value is in integrating that data immediately. The thermal map goes straight to the foundation engineer.
So if a drone spots a cold spot, an anomaly,
the engineer can adjust the design for that specific area before anything is built. Change the pile depth, use a different pile type, redistribute the load. It moves site prep from a manual survey to this highly intelligent preventative modeling operation.
It just proves that the most important structural decision can happen before a single shovel hits the dirt. Okay, so we've seen how buildings can interact with the atmosphere and the ground. Now let's scale way up and talk about governance, diplomacy, and how architecture can be an actual instrument of negotiation.
And this leads us to what is probably the most ambitious and politically sensitive project in the whole brief, the Hydropolitics Hub RFP.
This is for the Euphrates Basin in southeastern Anatolia. I mean, you're talking about designing for conflict resolution.
Absolutely. The project is for a Transboundary Water Governance Center. It's meant to be a place to coordinate water allocation between all the communities and nations that depend on the Euphrates River. This is where design meets resource scarcity head-on.
The brief says it needs treaty modeling halls, hydrologic simulation galleries. The building itself has to encourage trust.
Right. The architecture has to become a hydropolitical negotiation instrument. The very layout, the sight lines, how people move through the space, it all has to work toward a shared understanding.
The technical challenge here is fascinating. They ask for one spatial governance device plus one water data interface. So what does a piece of architecture that facilitates governance actually look like?
Well, the spatial device has to be about transparency and equality. So imagine the main negotiation hall is circular, no head of the table.
Okay.
And in the center, there's a monumental clear glass cistern. The water level in that cistern is a real-time physical representation of the collective reservoir capacity.
A shared reality device.
Exactly. You can't argue with it. It's right there. The resource they're all discussing is physically present in the room with them. It makes the abstract conflict totally immediate.
And the data interface, that needs to be just as powerful.
It needs to make the upstream impact on downstream communities tangible. So you could have a massive vertical data wall that uses real-time satellite and sensor data to show flow rates versus historical use.
But it has to be more than just numbers on a screen to be a political tool.
Right. It has to visualize the consequences.
So
So it could show, based on this upstream release rate, here are the projected crop yields for the downstream community next season. It turns complex data into a tool for mutual accountability.
That is just a brilliant application of architecture. Now let's connect back to our first theme, atmospheric intervention, but this time for public education, the Carbon Wind Exchange Pavilion.
So this is about taking that highly technical process of capturing particulates from the air and making it visible and understandable to the public.
And the design constraints are really tough. No mechanical fans. It has to run on the wind itself.
The structure can't block the prevailing wind, but it still has to produce readable environmental data.
So the building itself is the sensor.
It's a giant passive sensor array. Instead of screens, imagine the pavilion is made of tension fabrics that visibly flex or vibrate or even change color based on the wind speed and the volume of particulates they're capturing.
So the movement of the building is the data.
The physical movement communicates the wind's force, and maybe the kinetic energy powers some subtle lighting that shows the captured carbon load. The whole thing has to be incredibly porous, but still structurally sound.
An exercise in structural minimalism.
Absolutely.
Yeah.
Every single element has to be aerodynamically tuned to not disrupt the very thing it's trying to measure.
And finally, for this section, back to water and governance with the Hydro Atlas Learning Tower.
This is a vertical civic education tower. Each floor represents a different part of the water cycle.
Rain, fog, runoff, the aquifer, even drought.
It's meant to teach citizens about their local water system through a physical experience.
But the design constraints are huge. It has to be structurally self-draining. For a
Yeah.
high-rise building, that's a massive challenge.
It is. You can't just have a roof drain. The entire facade has to be a cascade system with visible channels and holding tanks. The fog floor might have these huge nets on the exterior that condense water vapor, and you see it trickling down.
And it also has to have a public governance function.
Which brings it all together. Maybe the top floor, which represents drought, is where the city's water crisis management team is housed. So as a citizen, you ascend through this educational journey about water, and you end at the place of ultimate responsibility.
The architecture literally connects scientific understanding to political action. All right, this is where we shift gears. We're going from these big picture projects down to the absolute micro level of structural physics. These are the hidden loads, the things you only learn about from these deep RE study blocks. Let's start with thermal and air movement loads.
These are the forces that are often, completely invisible, but they can cause huge problems over time. Take thermal stack acceleration pockets in high-rise elevator shafts.
Okay, why is the air in an elevator shaft a structural problem?
Because a tall shaft acts like a chimney. It's called the stack effect. In cold weather, warm air inside rushes up the shaft.
Right?
And that surge of air is so powerful it creates these localized pressure pockets. It actually pushes and pulls on the shaft walls.
And over time, that constant pressure can cause things to bend.
Micro deflections, yeah. And that's enough to affect the alignment of high-speed elevator rails, which is a huge maintenance and safety issue. The solution is something called plenum tuning, which is basically designing vents to relieve that pressure.
Wow. Okay, what about equipment heat bloom drift in a lab?
In any lab, Controlled airflow is critical, especially for safety around fume hoods. But if you have a cluster of hot equipment like ovens or sterilizers, they create a heat balloon,
A pocket of hot air.
and that hot air rises, and it disrupts the carefully balanced airflow in the rest of the room. It can cause turbulence in fume hoods or cross-contaminant experiments.
So the designer has to anticipate the heat output of the equipment that will eventually be in the room.
Exactly. You have to design the HVAC and the partitions to handle those thermal microclimates.
And this last one is really interesting, evaporative buoyancy shear in a swimming pool building.
Yeah, in a big natatorium, you have a massive amount of water constantly evaporating. All that rising moisture creates an upward force, a buoyancy. And that rising air creates a subtle but constant shear drag force on anything lightweight up high, like clerestory window frames or acoustic panels,
It's constantly pulling on them.
constantly pulling sideways. And if those elements were only designed for wind and gravity, that continuous upward shear will cause fatigue at the connections. Sealants fail, things start rattling. It's a great example of how moisture movement has to be calculated as a dynamic structural load.
Okay, let's move on to the silent stressors. Vibration, resonance, and repetition loads.
Yeah, starting with something you'd never think about. Localized microvibration islands in libraries.
A library. What's vibrating in a library?
Well, libraries now have these huge, compact, rolling shelf systems. And they also have equipment clusters,
Right.
copiers, scanners, archive lifts.
Ah,
That equipment creates focused pockets of vibration. And if the floor slab isn't stiff enough, those vibrations travel and can knock the sensitive shelving systems out of alignment.
and that problem gets magnified in a place like a data center with floor slab resonance.
This is a classic engineering problem. You have thousands of cooling fans all spinning in sync. They generate this rhythmic, harmonic vibration.
And if that frequency matches the natural frequency of the concrete slab,
That's resonance. The vibration amplitude shoots up. It can literally shake hardware loose, damage data, and speed up structural fatigue. The lesson is that mechanical repetition is a structural stimulant. You have to tune the slab so its frequency doesn't align with the equipment.
now, what about people? How can human activity be a structural load? The brief talks about public congregations cycle resonance in justice centers.
Think about a high-profile trial. The crowd has these repeating movement cycles. Everyone stands for the judge. Everyone sits. People surge out of the courtroom during a break.
It creates a rhythm.
A predictable, rhythmic pulse. And that creates lateral stress. A large crowd moving down a stairwell all at once generates a horizontal push and pull on the stair core. It's a dynamic load that's far more damaging than just their static weight.
Even solar panels can be a vibration source. Thermal pendulum restraint checks.
Yeah, so when you have a PT panel on a facade, the sun hits one side of the frame before the other. That causes uneven thermal expansion,
A tiny little bend.
a tiny continuous back and forth micromotion, like a pendulum. And over years and years, that constant vibration can cause fatigue failure at the mounting points if they aren't designed for it. Solar absorption is a structural vibration source. Who knew?
All right, third category here, material and geometric discontinuity loads. This is where different parts of a building are basically fighting each other.
And a classic example is lateral decoupling drift in a mixed-use building, where you have retail on the bottom and residential towers on top.
So the retail floors are wide open, not very stiff.
Right, they need big open spaces.
Yeah.
But the residential tower above has lots of walls, so it's much more rigid. You have a flexible diaphragm supporting a rigid one.
And during a wind or seismic event.
They want to move differently. The retail floor wants to drift further than the tower, and that creates massive stress and torsion right at the point where they connect. It's a huge design challenge.
A similar conflict happens in hybrid buildings with humidity-induced torsion drift.
This is in frames that mix steel and timber.
Okay.
Timber is hygroscopic. It swells and shrinks with changes in humidity.
Yeah.
Steel doesn't. So when a timber beam swells, it tries to twist against the rigid steel member it's bolted to.
So the wood is trying to warp the steel.
In effect, yes. It creates these internal torsional forces. The lesson is that you have to model how these different materials will react to the environment together. You have to design for environmental harmonization.
And in healthcare, we have sterile zone differential pressurization fatigue. That's a mouthful.
It is, but the concept is critical for infection control. In a hospital, some rooms need to be at a higher or lower air pressure than the hallway to keep germs from spreading.
Right.
But to maintain that pressure difference, the HVAC system is constantly pushing or pulling on the walls, the duct joints, the door seals.
Q4 forces them 365.
Exactly. And that constant low-level strain causes material fatigue over time. You have to design for it to maintain that critical sterile barrier.
Okay, our last microdynamic category, water and chemical interaction loads.
And this one is incredibly specific. Bidirectional salt spray crystallization. Checks on coastal bridges.
Wait, I thought salt damage was just salt damage. Why does the direction matter?
Because the wind speed and angle change how the salt particles hit the structure. On the windward side, the salt spray is driven in hard, it penetrates deeper. On the landward or leeward side, it might just settle more gently.
So you get different corrosion patterns on different sides of the same beam.
Asymmetrical fatigue. You have to map the microclimate's interaction with the bridge to accurately predict where it's going to fail first.
And for big infrastructure like stormwater tunnels, we have to think about multi-event hydropulse modeling.
Yeah, it's not enough to design a tunnel for one single massive storm,
Why not?
because excessive storms create cumulative pressure pulses. The structure doesn't have time to fully relax or recover between events.
So the tunnel kind of remembers the stress from the last storm.
It has a hydrologic memory, and that accumulated microdamage, that compounding shear, is what causes failures over long term.
We're now shifting from those invisible forces to some very real-world, high-stakes case studies from construction and management. This first one is about crane beam torsion waves at a port.
Yeah, this is a classic heavy industrial problem. A logistics terminal was seeing these measurable oscillations, torsion waves, in their massive crane beams.
2 to 5 millimeters of twisting back and forth every time a container was moved.
And they're moving 20 to 40 containers an hour. That repetitive off-center loading from the crane trolley, accelerating and braking, was literally twisting the 58-meter beam.
And the risk is huge. The crane could derail, the beam could fail from fatigue.
Absolutely. So the brief outlines this 5-step mitigation plan. First, you map the waves to find the peak resonance frequencies.
Then you add internal stiffeners damping diaphragms to absorb the twist.
And this is key. They reinforce the rail plinths with elastomeric bedding. It's basically a rubbery cushion between the rail and the steel beam that absorbs the vibrational chatter.
And then they actually changed the crane's software, recalibrating the speed to avoid those resonance peaks, and they added sensors for real-time monitoring.
The lesson is just so clear. This kind of architecture is a dynamic structural theater. You have to design systems that not only bear the load, but actively capture and mitigate the waves that repetition creates.
Okay, now let's talk about the impact of climate on the construction process itself. Micro-shear slippage in prefabricated walls.
This is a great case study about timing. A mid-rise building saw measurable slippage between its prefabricated shear wall panels.
But it wasn't from wind or an earthquake.
No, it was from a rapid temperature swing. The temperature went from 9 degrees Celsius to 28 degrees in just 36 hours.
And the different materials expanded at different rates, too fast for the connections to handle.
Exactly. And you get 1.8 to 2.3 millimeters of slippage. And if you don't fix that, it adds up and starts misaligning elevator rails and everything else.
So the fix is all about prevention.
It is. Adding friction brakes between the panels, but also, and this is crucial, installing temporary bracing, specifically during periods where you expect a big temperature swing. The takeaway is that temperature is a structural scheduling factor. You have to time your installation to the climate.
We're going to end by connecting building code back to all this structural dynamic talk with egress with compression.
Right. The insight here is that egress design, like for a fire escape, isn't just about a static width measurement. It's a crowd physics problem.
Because when people are moving urgently, they don't flow smoothly, they compress.
They form pressure zones.
Mm-hmm.
And the brief points out that the geometry makes it worse. A curved hallway dramatically reduces the flow rate compared to a straight one of the same width because people bunch up on the inside of the curve.
And it gets even worse on stairs with weird riser widths.
It does, because that disrupts people's natural rhythm, which causes more bunching and creates choke points.
And this connects directly back to our earlier point about courthouses. When a courtroom lets out or there's an emergency, you get a crowd surge.
And that surge loads the stair core laterally. Human movement becomes a dynamic load case that the structural engineer has to model, not just a simple occupancy number.
Wow. This has been an incredible deep dive. I mean, we started at this massive global intelligence level.
Talking about permafrost thaw and transnational water politics.
And we ended up talking about the forensic details of vibrations in a library or a swimming pool.
And the synthesis, the through line is so clear. All of this knowledge is pushing the designer toward embedding intelligence and elasticity into every single decision.
From adaptive facades cleaning the air to foundations stabilizing the earth.
To a negotiation center designed to literally facilitate diplomacy.
And the takeaway for you as a designer builder is that you have to see every building as this highly calibrated system that's reacting to climate, geology, and human behavior all at the same time.
You're not designing static boxes anymore. You're designing responsive, dynamic interventions. And the only way this knowledge has value is if you understand it and you apply it.
So, as you go back to your own work, we want to leave you with the core philosophical challenge that was posed by this amazing mentorship briefing from the services of KING-KAMBUF PS Architecture. You need to ask yourself this question. How can the built environment act not merely as shelter, but as an atmospheric, hydrologic, and political instrument? What is the next generation of intelligence you can embed in a structural decision to make that building adapt, absorb, and respond?
Thank you for joining us for this deep dive into architectural insights with King-KAMBUF.
We'll see you next time on Beyond the Comfort Zone Talking Shit with KING-KAMBUF.